So, good morning and welcome to this second lecture in this module on adaptive signal processing with the course electronic system and applications. So, today's lecture we will look at a brief review of random processes relevant to the adaptive signal processing aspects. So, why do we need to look at random processes? So, recall from our previous discussion, the systems which we are interested in usually have in signal which we are interested in, which is denoted as d of n, which is the desired signal. Usually this is due to some real world scenarios. It's assumed that there is some corruption or modification to the signal, and the signal we are hence observing is, let's say, this x of n, right? So this x of n is a signal which can be thought of as the desired signal d of n plus some signal which arises due to this corruption. So this corruption, for example, as you would have seen in the lectures on sensors, depending on what you want to measure and depending on the quality of the sensor, there could be different modifications happening to the desired signal, and that is the observed signal x of n, right? So this modification or corruption which happens in most real world signals has to be understood slightly better so that our design system work well with such corruptions. So a more notional way of saying this is this we will refer to as noise, and typically these noise we need to characterize, and hence these are not some deterministic signal, and hence we need to bring in this notion of random So this notion and understanding of some basic aspects of this random process will help us understand these systems better. So what we will see today is, for example, you are trying to measure temperature. So while the actual temperature may be a d of n, there could be noise due to the sensor which is being introduced. You could characterize in some way which could be the noise. We will have to see what kind of noise does the sensor introduce. If it is not the sensor itself, it may be in the process of, let's say, you are measuring a continuous time signal which is the temperature, and then for our processing we are going to look at a discrete version. So in that sense, maybe there is the process of A to D and then quantization, which all introduce some variation to the original signal and which could be described as a noise, which could be quantified as a random process. Hence that's the motivation for trying to look at random process. We will not do an elaborate study of random process. We will look at things which are relevant to understand these adaptive signal processing better, right? So before going into this random process itself, I'll just briefly say what these random processes refer to and how would we handle them. So this notion of random process, before getting into random process, we need to just briefly look at random variables. I'm hoping that all of you have some prior knowledge and background in probability and statistics. So this is not again just it's not an exhaustive review. This is just to say how these random variables help us understand some aspects of adaptive signal processing. As we know, so random variables can be thought as something which map from an experimental outcome to some real numbers. Of course, this could be also complex, but depending on what experiments we consider and how we treat these random variables. So for example, a random variable x will define as a mapping from some omega to set of real numbers, where this omega is outcome of a certain experiment. Of course, if you consider the coin toss experiment, then this could be omega would be heads and tails. So these are the possible outcomes, and each of this is an event, and how to map this event such that this event has occurred is done using this random variable. For example, we could say we want to describe, let's say, what is the probability that the event H, which is the head, has occurred. Right? So instead of saying this, what we do is we'll say we define RV, let's say random variable X as follows. X 1 head occurs, X minus 1 tail occurs. So this is that X equal to 1 indicates a event H occurring or the head occurring, and event X equal to minus 1 indicates a tail occurs. So now we could define probabilities and say, for example, for a fair coin where the probability of having head and tail is equal, we will denote as so. This is just to kind of say that this is what a random variable is. While this is itself useful for us, what we are more interested in is in random process. The reason why we are interested in a random process is we are interested in how things change or vary with time, and to capture this notion of time we need to bring in this random processes. Before going again into the actual definitions, so let me just briefly use some figures to just show what we mean by this random process. So random process can be thought of or actually are defined as a collection of random variables and indexed by a set. So for example, let's say this one could denote this as, let's say, xi of n, where n is a time variable and I indicates what is referred to as a random ensemble of a random process. One way to look at it is, let's say we consider a space. There could be several these are different realizations of a specific random process. So for example, this could map to one ensemble in a, of course this has to be a discrete version is what we are interested in, but if you just consider this to be, let's say, this could be another realization. So these are n, this is our x1, this is x2, x3. So these are so for us this index can be any index, but since we are looking at processes which vary with time, so for us we will consider time as the index which is of interest to us. Okay. So now if I am talking about let's say statistics of this random process, typically the way to look at it is to, let's say, you consider a specific time or index. Let's say, for example, in this case index n0, and then when we say about mean of this random process, it is the mean across these ensembles at this time n0. So you can see that if we say about mean, similarly the other statistics also could be defined depending on which statistics we are talking about across different instances. Right? So I could say something about at n0, then I can say something at, let's say, n1, and then say how does the behavior of the process change with time, let's say from n0 to n1. Right? So then this brings us to the notion of if we know something about the process at n0, can we say something about the process at n1, or is this completely uncorrelated, or is it correlated? Right? So these are the notions which are going to be of interest to us. And so of course, as I mentioned, I have shown a continuous plot here. Typically we are interested in a discrete version or a sampled version of this random process, and that's what we are going to look at. So with this brief, so what we think is, if we conduct an experiment, what we would probably get is one such outcome, right, or one such process, right. But the statistical properties of this process, if it is assumed to be from the same process, they remain the same. So maybe this random process would have certain mean and certain variance, which we compute over every time index. So that's kind of quick start for what I wanted to talk about in this lecture. And now let's look at more specific definitions, and so that when we actually look at problem setups, things become more clear. Okay. So we'll revisit this plot little later, and let's go back to our slides. So as I mentioned before, what do we indicate by random process? It's an indexed collection of these random variables, and for discrete sequence we refer this as x of n. So this could be an outcome of an experiment. So for example, measuring temperature in one room and then keep on measuring temperature in other room, and among a list of possible, that's the ensemble. The ensemble when we measure today, measure tomorrow could also be one realization of the ensemble, and we want to characterize such measurement, right. So how do we let's say, so each of this thing is called a realization. So now when we want to, why are we interested in this? Because we are interested in the underlying model which represents this thing which is happening in the physical world, and hence this is the process which we are trying to characterize, right. So what are some of the statistics of relevance and importance which we have to look at? One, as I indicated previously, is the mean of this random process. So the mean, from a notation sense, we use this notation of m to indicate mean, x sub to indicate the process, and n is that index variable which you are using in this case time, right. So this is like as in standard probabilities, this E represents the expectation, this curly braces here represent that it's a process, and by this we mean there are many ensembles or realizations of this process. So, this mean we refer is the mean across these ensembles. So, this mean relates to one specific time. So, extending this to the same process at two different times, let us say for example n1 and n2. So, we have this function which we refer as this autocorrelation function, which is essentially the mean at n1 and mean at n2. So, this in convention typically there is a conjugate assuming that this random process could be complex, though most of our discussion will be using real signals, but for without loss of generality it is okay to say that this is a complex conjugate of this x of n2. And so, this is just how we define. We will later see how these things can get simplified, but depending on the kind of process we are looking at. Right? Similarly, if we consider variance, which is the deviation from the mean and then across n1 and n2. So, this is the deviation from the mean at n1, which is the first part here. The second part here is the deviation from n2, which is mx n2, which is the mean at n2. And so, this joint distribution or function is referred to as this autocovariance function. So, the difference between the correlation and covariance is essentially non-zero mean. In many cases when we look at, it is always possible to take a non-zero mean random process and make it a zero mean process. So, mostly we will be looking at and handling autocorrelation functions and not do too much with autocovariance function. So, while this is the general description of random process, the process which we are usually interested in and we want to characterize has certain properties, which means typically the statistics not the value itself, statistics of this process remain same over time. Okay. So, such a process, which means if I take the process and delay the process by some time, statistically they are indistinguishable. Okay. So, these are called as a stationary random process, which is of importance to us. To give more specific definition, so you can think of the joint distributions across all these time intervals, time samples, let us say n1 to nk. Then if this joint distribution is same as a delayed version of this joint distribution, then that is one of the kind of strict properties which ensures that this process is stationary. More specifically, for such stationary process, the mean will remain constant over time, and since it is constant over time, it is typically the mean at, if you think of the 0 index, that is the mean at 0 index, that is the mean. Extending this to autocorrelation, what will happen here is in this stationary process, they are not just time independent, it is just a time difference dependent. For example, here we look at L is the lag. So, if there is a lag of L samples, then the autocorrelation across these L samples or samples which are delayed by L is what is defined here. This only depends on the lag, that is how far away the process is or the sample is separated from a given sample decides how much they are related or correlated or uncorrelated. So, that is the kind of indication. So, typically it is enough to say when you are talking about stationary processes, just to mention the deviation or delay, or in another word just the lag. Okay. So, this n1 minus n2 will just be the L which we mentioned here. So, usually it is an Rx L is what we are interested in. So, this is kind of a strict sense of stationarity, in the sense we expect this to have this joint distribution to indistinguishable across time. There is a slight relaxation of this condition, which is what is more useful in practice. We denote that using what are called as this White-Sense stationary random process. What are White-Sense stationary random process? They are subset of this stationary process. Only thing is we are not talking about the joint distribution, instead only we are looking at two first order and second order statistics. So, the mean as in the stationary process will just remain same for all n. And if you look at the autocorrelation is only a function of this difference between n1 and n2, or it is only a function of the lag, right. So, this is the term which we will use more, that lag essentially indicates how much two samples of a process are separated or distributed away from, So, with this notion of, so these properties of mean and autocorrelation of the process or quite useful, so that we could describe many of the noise which happens in practice using some probability distribution, and then many times they can also be assumed to be either Whites and stationary or stationary. More often we will think of them as Whites and stationary, reason being so expecting to having a joint distribution to remain unchanged is difficult in a practical scenario. So, I am not going to spend more time on the properties of the autocorrelation function itself. I recommend that you do refer to the one of the standards which books which I had referred to, could be the Hayes book. So some properties which are of importance is the symmetry property of correlation as in signals. So, this correlation is conjugate symmetric. So, if you look at the negative lag, then it's conjugate of the, if it is a complex number, it's conjugate. If it is not complex, then you can see that this is just a symmetric function, right? Autocorrelation function is a symmetric function. Note again, here we are only using this for Whites and stationary, since we are talking about only the lag part, right? Similarly, another property which is of use later is, so this correlation function at the value 0, which is saying if you take two random processes and just overlay on top of them, that's looking at this kind of cross correlation or autocorrelation. So, you can see for no lag, the sum of all that products will peak, and that's what this is essentially saying, that the autocorrelation or correlation at the 0 lag is the maximum. So, these are some conditions which you could check to see if the process is a valid, if a given sequence is a valid autocorrelation sequence or not. So, moving on, this notion is probably going to help us later when we look at representing systems and then signals which are input to the system. So, rather than taking just a random process as one variable, we would take it as a vector and say that it is this as given here. So, before, I think maybe one aspect which I would probably bring to attention before going on with this lecture is, this other remaining parts of the lecture is this notion of ensemble and time averages. We will have a representation little later, but maybe I will just kind of switch to this white sheet to go through it once. So, this is to just bring in that the notion of ensemble. I am just using this word slightly loosely, but let us say that's ensemble statistics versus time. Again, this is probably not the exact way which is referred to in literature, but so I wanted to talk about one specific notion and then which will be useful later, right. So, one thing, as I mentioned before, we were talking about is ensembles, right. So, just to be specific, let me just have discrete versions of this random process just to be relevant to what we are discussing. This is some realization of this random process. So, let us say it is x1 and then there is this second realization. Assume they come from the same, these are from the same process. Of course, these are not the deterministic signals, so there may be many such ensembles, just as an example. So, this is again it's good. So, these are different ensembles, and what we were talking about is this ensemble statistics is this one, right. So, if I take a time n0 and time n1, we could look at mean at n0 or mean at n1, right. So, these are, let us say, ensemble statistics. So, I guess it is. So, this that is we are taking across time and saying, right. But so let's, if you look at our practical application, So, it is not that our system is just going to wait for all these possible ensembles to happen, right. So, most times we only have access to one of these realization, right, because that's how the system is operating. So, maybe depending on the time we have access only to this realization, right. At a given, the same notion of time, but let us say at a given period or a given day, whatever that is, right. So, now when we want to make statements based on just this, we need some kind of relation between this ensemble statistics and what I call as temporal. So, for example, what we mean by temporal is if I move across time and I look at the statistics. So, for example, maybe I take an average, right. So, this average across time is not necessarily the same as the average across a given n, right. So, these two statistics are different statistics, and we want to make sure that when we use this one sequence to understand some of the statistics, they kind of match the ensemble statistics. So, we are usually interested and consider what are called as ergodic process. Okay. So, what do we mean by this ergodic process? So, I think we have a slightly defined more precise definition later, or even if not, let me just say here. So, this is saying, for example, if I take the mean across time, that mean across time is same across the mean across the ensembles, right. So, it is not just the mean, it can be mean ergodic or autocorrelation ergodic. So, if it is autocorrelation ergodic, it is saying if I take two ensembles across the n0 and n1 and I compute an autocorrelation, this is same as the autocorrelation if I just take this sequence and consider the statistics between two lags n0, two time samples n0 and n1, right. So, if these same, that is if the mean and the autocorrelation are same, whether you look at the temporal statistics across one process or you look at the ensemble statistics across many such ensembles, then we refer that as ergodic, and most discussions which we will have will assume that this, that is by looking at one given realization and understanding and estimating the statistics, we are assuming that statistics describes this entire process, that is it describes the ensembles of this process. So, that may seem like a very strong assumption, but that is not really that strong because that happens in practice many times. But the reason why I wanted to just bring in here is, so now I am going to talk about notations wise. So, in notation, while we discuss a random process, we may say we may index it across time or indexes across ensembles. We will use this notion as if that there is one process and we will use samples from that process. So, in that case, then it will become you have to be careful as to which of this is being indexed. Is it the ensemble being indexed or is it the time being indexed? So, now let us come back so that we have the notations a little bit more clear. Yeah. So, when we come back, so here we see this x is a random process, and as mentioned here it is a process of n samples. So, it samples across 0 up to n minus 1, right. So, these n samples are samples from the random process, but in practice this may be that these n samples are just from one realization of that random process, right, that one ensemble of the random process. But for definition that is not very critical, but just as long as we understand that when we implement such things, we may be actually getting all this from one realization, right. So, similarly, if you look at the mean is again the expectation. This expectation here typically refers to the ensemble means. It's like saying mean at 0, mean at 1 and mean at n minus 1, so on. And if you see, if you are considering wide sense stationary process, then this will all be one value because the mean does not change with time, right. So, moving on from mean to autocorrelation or correlation. So, this notion is something which we will again use a lot. This is the outer product of x and x conjugate, or x Hermitian if you want to think. So, this is called as the autocorrelation matrix. So, typically depending on the number of samples you use to denote X, you will be that if it is n, then you will have n by n autocorrelation matrix. The structure of the matrix is shown here. So, this is just applying expectation over this X transpose, which is what is denoted here. Now, if we kind of try to simplify this autocorrelation matrix by considering this as a White-Sense stationary process and also using properties of autocorrelation function. So, you exploit this symmetry and conjugate symmetry, and accordingly we will end up with saying Rx0, Rx minus 1 up to so on. And if you really closely look at it, if you exploit this properties of symmetry, this Rx minus 1 will be same as Rx1, and similarly across all these lags, and accordingly you will see all these diagonal elements here already are 0 is same, which is the signal energy which is denoted as Rx0. Similarly, the other leading diagonals Rx1 and this downwards, Rx minus 1 and then downwards, they are also same, right. So, this is a kind of a special property of the autocorrelation matrix, which so as you mentioned here, its elements in the main diagonal are all equal. That will refer to as, actually all diagonals are equal. So, this is referred to as a Toeplitz matrix, right. Not just Toeplitz, that is not just the diagonals are equal, but it is also Hermitian symmetric, that is if we conjugate and transpose, this matrix remains the same. So, this matrix is a Hermitian symmetric and Toeplitz matrix. So, this property can be exploited when we want to do some, let us say, inversion of Rx. So, these matrices have some algorithms which you could use to obtain inverses efficiently. Rather than doing an order n cube inversion, we could have some algorithm which are less complex computationally and achieve them in, say, order n square. When we revisit this in terms of implementation, I will just mention at that point, but for now I think sufficient to know that this autocorrelation matrix typically have a good property. An additional property was, we saw previously this Rx 0 being the largest among 1 and it is going to be positive. So, we will also see that this autocorrelation matrix will be a positive definite matrix. So, these are some properties which are autocorrelation matrix which will be useful later when we come back to use them. So, this set of slides maybe will be uploaded along with this lecture, but these parts are not necessarily relevant, but for those of you of interest in finding how do you characterize further this random process, do take a look at this spectral density, which is like power spectral density. So again, I am not going to spend too much time on the power spectral density, because I am assuming this is something which you have already done, but since to make this complete, so when we are characterizing our random process, one thing which is of interest is what is the energy in this process, right. Since random processes are non-finite energy, we can't apply DTFT directly. So, we look at DTFT or FFT of the autocorrelation sequence, right. So, that is again why the autocorrelation sequence of random process is much more important than just looking at the random process itself, right. So, this power spectral density helps us characterize the random process in a way, let us say the energy and power of a deterministic signal help us characterize this deterministic signal. So, in that sense this is useful, and once you know the input power spectral density, we would also want to relate it to the output. So, just to define, so the power spectral density is defined as the Fourier transform of the autocorrelation sequence. In this case, it is a DTFT of the autocorrelation sequence, since we are considering discrete time sequence, and this is valid for the White-Sense stationary process. So, the other definition also comes directly from deterministic signal, that is, you take your set of samples, you find the DTFT. Since this is a random process, that finite set will not give you the right estimate of this frequency content. So, you look at many such in realization, right. So, then this kind of helps us obtain, in this case, the power spectral density of a random process. So, as mentioned here, the differences is the finite stum become an infinite here, and then we have an expectation here to handle many such short segments of the given realization. So, this I had previously just indicated. So, this also come directly from the autocorrelation sequence and the power spectral density of the autocorrelation sequence. Following from the power spectral, so from the autocorrelation sequence, since the power spectral density is the Fourier transform or DTFT of that sequence, some of these properties also follow, that this power spectral density is always real, it's non-negative, and symmetricity of the autocorrelation sequence also follow into the power spectral density. And since it's a frequency dependent function, it's periodic with 2 pi. This notion, which is at the end referred as effect of filtering, is something useful. So this is to say, if there is an input signal into a system H, and if its power spectral density is Px, what is the power spectral density of the output? So that essentially says that if you know the frequency response of the system, it's the square of the magnitude response of the system. So here, of course, it's not very difficult to show that what is this? This is, let's just go back to this slide here. So the reason this is of interest to us is we will typically look at let's say some signal going into some system, and we will have an output from this system. So this system may be characterized in different ways. Let's say if you consider it's a LTI system, let me it has a frequency response, and we want to relate this x of n to y of n. X of n so or in our case it could be a noisy input signal, and this is trying to do something, and we want to look at what is y of n. So this notion of signal going through a system is important to us, but momentarily if we just look at this as an LTI system, we could look at, but the inputs are still random process, then the output is also a random process with certain properties, and one of the properties is we want to relate the autocorrelation of the output, if you know the autocorrelation of the input, given the system response, right. So one, and then correspondingly in the Fourier domain we will have, if you look at the power spectrum of the output, let's say you denote it as this P y e j omega. So this can be related to the magnitude spectrum of the LTI system as this. So why is this important? This is important because if I know the input power spectrum, I can know what the output spectrum is, right. So in the input spectrum is noise, I will know what is the power spectrum of the noise. You can see what is the effect of this system on this noise, and that would be the output power spectral density. So this notion of taking, let's say, I mean you can always look at and say that okay, what is this output? This output can be thought of as, if since this is an LTI system, we can think of it as and say it's a convolution of this x of n with h of n, right. So from x of n to h of n, if you get y of n, then what we are interested in is what is or y of, let's say, k, assuming this x of n is white and stationary, what is or y of k, that is what is the autocorrelation of the output sequence if you know the autocorrelation of the input sequence and the filter, okay. So you should be able to show this just by applying the expectations and convolution, what this r y should be, and from r y you should be able to do the DTFT and say that okay, this DTFT is essentially the magnitude square times the input power spectrum. So that essentially is what I wanted to talk about in terms of random process. So just as one example, just to kind of bring out the difference between the ensemble average, why is it important, versus the time average, why could it be different, right. So that's I'll just give one example and then maybe I'll stop with that. So what is this so let's just consider a signal x of n. this is just a sinusoidal signal. A is random variable. It's a uniform. Assume this A takes on these two values, either 1 or 2, and then this is the process which we are interested in, right. So, one thing to just clarify is, see, there is the only random here is this quantity A, and apart from that this is all deterministic part, right. So, you can think of now what will happen if I take just one realization of this. So, that realization may have A either 1 or 2, let us say it has 1, then remaining will be just the cosine signal, right. So, what will happen to the, just think as to what happens to the temporal mean of one realization of this process, right. So, what will happen? So, it is just more like a cosine over a long time. So, irrespective of what this A value is, so this expectation will be, let us say I will denote this as temporal. So, this is going to be approximately 0, because over time we have an average over the cosine, and that is going to be just the 0 value, right. But instead what about the ensemble mean, right. So, this is the mean, we say that given any given n, it's an n0, n1 or n2, to find the mean of that process, right. So, if you take a mean of this process here, so what would that be? That would be, if I just say that is m ensemble, or that is actually the typical definition of the mean of a random process. So, that is just going to be the expectation of A times this cos n omega naught, right. In this case, if it is uniformly distributed, then we have, let us say 1.5 cos omega naught, right. So, you can see in this case here the mean is kind of time varying, and whereas here the mean is just a constant 0, right. So, this is not a ergodic process, and so when we are applying our statistical distribution descriptions to this process, we have to be careful. So, what I wanted to just say is, I think one aspect which you have to become very familiar and comfortable with is, given any process, you should know whether, first of all, it's is it a Whitesian stationary process. If it is a Whitesian stationary process, you should be able to estimate its statistics and see whether you have enough to estimate the statistics. And if nothing more is said about the process, then you could assume that this ergodic nature is true, and you can make all your inference based on that process description. If something is said about the non-ergodic nature, then you will have to be careful about how to analyze such system. So, it will certainly help doing examples in this random process and autocorrelation sequences. So, I recommend that you do such things, get familiar with this notion, and so that gets prepared, that makes us prepared for the next session, which will, where we will actually get started on looking at some basic adaptive systems, and before actually going to the adaptive system, we will look at an optimal system which can do what we want expect to do. So, thanks for listening, and that is the end of the module on a brief review of random processes. We will meet in the next one. Thanks.